right, good morning, guys. On Monday, we started doing a little tour through the primary modes of heat conduction, right? Our conduction, our convection, and we ended there. Because, as you may have noticed, I tend not to finish the lectures that I have planned. So today, I believe we will actually get through all of this. Here's hoping. But what I want to do today is wrap up our discussion of the heat transfer modes, specifically by talking about radiation and doing an example that involves a combination of different heat transfer modes simultaneously. And then we're going to loop back around to start looking at conduction in greater detail, because that's going to be the next kind of big chunk of this course is going to be focused on conductive heat transfer. So we'll be delving into this and actually looking at how we solve for temperature distributions and heat transfer rates in more realistic engineering problems. So so we want to conclude with our discussion of radiation. We want to be able to describe multi-mode heat transfer. And we're going to just start our detailed look at conduction. So, what we've dealt with in terms of our types of heat transfer so far are conduction, right? That diffusion of thermal energy, notably that diffusion of sensible thermal energy, that is the energy that's captured in the motions of our molecular structures, and that diffuses through a medium by spreading that energy out. So anytime that two media are in contact with one another or inside of a given medium, you're going to have this diffusion of thermal energy, which we call conduction. And we discussed the fact that it relates our heat flux, our Q double prime, to the temperature gradient inside of that media. Convection, we said, is a combination of conduction. So if you have a fluid next to an object, some of that heat or some of that thermal energy is going to be transferred through the fluid by those adjacent, molecular structures and the diffusion of energy. But at the same time, you're going to have motion of that fluid, or advection, which takes some of that warmer or more energetic fluid and sweeps it away and replaces it with cooler fluid, or vice versa. Maybe it's doing some heating instead of cooling. And so the combination of these two things, the conduction and the advection, we group together under this moniker of convection. And this gives us a heat flux that is proportional to the temperature difference between our solid and our fluid times a convection coefficient. And it's going to be sort of the middle 1/3 of this class dedicated to figuring out that convection coefficient for different types of flows with different fluids in turbulence and laminar flow, etc. And this is really where we're going to be injecting a little bit more of our fluids knowledge into the course. The third mode, which we didn't get to on Monday, is radiative heat transfer. And this is a kind of a different animal, right? So this describes the energy transfer by any medium at a non-zero temperature, by means of electromagnetic waves. So basically, any object or any matter, whether it's gas, liquid, solid, if it is at any temperature above absolute zero, then it's throwing off photons. Okay? These photons are taking energy with them. And it's a really interesting means of heat transfer because it seems at first glance to almost violate our second law of thermo. Right? We talked about our second law of thermo says that thermal energy does not spontaneously flow from colder regions to hotter regions. Right? It has to kind of go downhill in terms of our temperature distribution. But we're going to show sort of through some logical inferences that, for example, any of you that walked outdoors this morning, technically you contributed to heating up the sun. Okay, and that's through this process of radiation. And it's a really counterintuitive concept, but it's something we're going to try to work our way through. So the first thing to know about radiation is that it is most efficient in a vacuum. And the reason for that is that there's no matter to absorb some of those electromagnetic waves in a vacuum. But it'll take place in air as well, right? So I want us to consider a surface, right, that has some temperature, okay, Ts. Now, there's two types of radiation we're going to consider. That is the incoming radiation. Okay. And we give this the variable name G. So G is what we call irradiation. And that is energy in. And we also have outgoing energy, which we'll call E. And we call this the emissive power. Okay. Energy out. So here's the thing to understand, is that radiation it doesn't care what is receiving any emitted radiation. So this emissive power depends only on this surface here. This is where I made the statement about everyone here warming up the sun a little bit, is that assuming you're walking around and your temperature is above absolute zero, which it tends to be for us, you are radiating thermal energy, okay? And it's just blasting out there, and anything in its way is going to see that as incoming irradiation, okay? So, yeah.
Kind of just like a quick question. So, since we're like in the atmosphere, and you said it like it's takes place most effectively in a vacuum.
Mm-hmm.
So, like in like space outside of the atmosphere, like would it act differently?
Yes. So, if you're in atmosphere, then some of that irradiated, actually probably a vast majority of that emissive power that's coming off of every one of us or any object that's above absolute zero is actually going to be absorbed as irradiation on the fluid, the air that makes up our atmosphere. Some of it is also going to be like reflected back in by the various layers in the Earth's atmosphere.
So, well, okay. So like, I guess like how differently would it act like as if it was like on the surface of the moon, like the atmosphere?
And you would emit the same amount,
Okay.
but more of it would like there's nothing for it to run into. Think of it that way. There's no molecular, like there's no matter between you and whatever's on the receiving end of that radiation. And so there's going to be more of that shows up as irradiation to any object that can, see you. So the surface emissive power, right? This quantity E. We express this in terms of how close to what we call a perfect radiator something is. So let's introduce the concept of a perfect radiator is known as a black body. Okay. Reasons for this is that things that tend to, like the surfaces that are black tend to be better at radiating and better at absorbing energy. So there's sort of the ideal in terms of their absorption of all wavelengths of electromagnetic waves. And the radiated power of a black body can be written as E sub B is equal to sigma times that surface temperature to the fourth power, where sigma is known as the Stefan Boltzmann constant, and is equal to a value of 5.67 times 10 to the negative 8th watts per meter squared Kelvin to the fourth. Okay. So we want to write down, make sure we have this idea of the black body radiation, have our Stefan Boltzmann constant. The Stefan Boltzmann constant is actually a little point of trivia. It's hyphenated, not because it was discovered by somebody whose last name was Stefan Boltzmann, but it was independently come up with by two people. Josef Stefan found it empirically. He basically he used it by studying. It was like the wavelength of light emitted from objects at different temperatures, and Boltzmann, I forget his first name, derived it from first principles, and they got values that agreed almost exactly. Okay, and so this is one of the most, I'd say probably one of the most successful empirical constants derived and then later verified theoretically and through continued observation. Thing is, very few surfaces behave as the perfect radiator. Okay? And so they're assigned some sort of some efficiency factor. So the E of a real surface is going to be the product of epsilon times the black body radiation, or epsilon sigma times the surface temperature to the fourth power, where epsilon is known as the emissivity, and falls in a range of 0 to 1. So this basically tells you the efficiency of a radiative surface relative to this perfect, right? This ideal of a radiator. So that gives you the key. Okay, if you know the emissivity of a surface, and these are generally quantities that we're going to be given. If we know the emissivity of a surface, say 0.6, and we know its temperature, then we know how much energy it is radiating, or how much, we should say, how much power per unit area it is radiating. So what its heat flux is going to be. So next, let's examine this irradiation, okay, G. So we saw that like G is any incoming power, but how much of that power gets absorbed by a surface is likewise going to depend on the character of that surface itself. So a perfect absorber would also be, like a black body is also considered a perfect absorber. So if the sun is irradiating the surface of the Earth with some power per unit area, G, a black body will absorb all of that. But a mirror is going to absorb very little of it. And the difference between those two things, between those two surfaces, is what we call it's like we have the emissivity. In this case, it's the absorptivity. So G absorbed is equal to alpha times G, where alpha is also between 0 and 1 and is known as the absorptivity. Okay, so what this means is that with these two kind of ingredients, our emissivity, or our emissive power and our absorbed irradiation, we can figure out what the rate equation for radiative heat transfer is. All right. This becomes Q double prime due to radiation is equal to simply, E minus G absorbed, right? This is signed positive out. So times the unit vector. So this becomes epsilon sigma surface temperature to the fourth minus alpha times G in vector. So here is where we can take a moment to examine what the implications of this equation actually are. All right, this is where I'm saying that radiation is a different animal than convection or conduction, because in those cases, heat only goes in one direction, or thermal energy is only in one direction. This is always, or almost always, a mutual exchange of thermal energy, represented here. So your surface, sitting here cooking at whatever temperature it's at, is throwing off electromagnetic waves in all directions, and anything in the path of those waves is going to see that incoming radiation, okay, and absorb a portion of it. So we're throwing off radiation. Some of it is attenuated by the atmosphere between us and space. That little bit that makes it to space, a tiny little bit of it hits the surface of the sun, and the sun is going to absorb some finite quantity of that, and therefore we contribute negligibly, but a little bit, right, to heating up the surface of the sun. But from our perspective, right, it doesn't matter whether there's a sun there or whether there's a mirror there or there's air there. We're shedding that energy. We don't care what's on the receiving end. Okay, so what is there to absorb does not affect how much emissive power is there. On the other hand, we're going to be getting irradiated substantially more, right, by the incoming radiation from the sun. And, right, every other surface that is within like a line of sight that is above absolute zero. So we're all absorbing incident radiation from every other person in the room, from the projector, from the walls, okay, from the air itself. So this is one where we really need to think carefully when we're setting up problems involving this, involving radiative heat transfer, about where energy is coming from, and it can set up these really complicated exchanges if you have multiple surfaces. Yeah.
So is this just specific to heat, or is it also valid
Like other radiated energy? So I'm not an expert in terms of other frequencies, but most waves, okay, are just electromagnetic waves, right? Light, magnetism, okay, FM radio, and thermal energy is just one kind of band. And so, yes, I'd feel pretty confident in saying that this is true of any type of radiated energy. But I'm going to have to claim ignorance beyond the bounds of heat transfer. So I can't answer that with total confidence. Okay. So there are a couple of modifiers here. Oops. So we talked about the fact that radiation is most efficient in a vacuum, but we don't tend to exist in vacuums. So how does the air that surrounds us play into radiative heat transfer? So if we have a surface, okay, and let's say we've got some radiation source. This could be the sun, right? This is some T object. This is at our TS. And we have some fluid, okay, that is flowing between these, that is at T infinity, okay? This is going to be radiating energy, no modification to that. Okay. It's going to be, right, there's going to be some E. There's going to be some radiated power coming from T object that hits our surface. So we could call this, G object. But our gas or our liquid here is also going to be radiating some energy, right? It's at a non-zero temperature. At the same time, it's also going to be radiating some energy, and we don't really want to have to add further complication. Okay, let's call this G, right, of the fluid. So fluids also participate in radiation. But we don't want to have to further complicate it by figuring out how the volume of this fluid is mutually radiating energy, how much of that makes it to the surface. That has the potential to be an incredibly challenging problem to solve. So what we tend to do instead is we wrap up that radiative heat transfer as a little modification Q, right, both convective and radiative, right, between the surface and the fluid. I know there's a complete monstrous subscript there, becomes this H combined, right, times our TS minus T infinity. So what this means is we're making an approximation. We're basically linearizing this fourth order relationship, that describes how much radiated energy occurs as a function of surface temperature. And we're throwing it into this H combined so that this does a fairly good job of also capturing the net energy transfer through radiation. So this is a pretty common approach whenever you have radiation in fluid surroundings, is you'll get the fluids part of that radiative heat transfer wrapped up into this convection coefficient. And so the way we would handle this then is we would get rid of this G fluid, we would have pure convection between the surface and the fluid, and pure radiation exchange between the object and our surface. So it sort of decouples our problems. We're going to do an example of this in a moment. There's one other special but very important case. Which is a small surface contained in large surroundings. So I want us to think of T surroundings, TS. This is our surface with, a surface area of A. And so a good example of this is kind of any surface that's like out in open space, outdoors, because we can treat the sky as being kind of this model of surroundings. Or if you have a piece of electronics that's enclosed inside of some, enclosure. And there's a few things that happen when this is the case. One is that those large, that large surrounding surface acts like a black body. Okay? And this is something we're actually going to show later on in the course once we hit a radiation section. But you tend to get perfect emissivity and perfect absorptivity out of these large surfaces. So the night sky, in a sense, will absorb all the radiation you throw at it. And then the small surface acts as an imperfect radiator with an emissivity equal to its absorptivity. Okay, so it's got kind of the same efficiency at absorbing and at radiating compared to a black body. And this is a special type of surface that we call a gray body. So in this case, which, like I said, we see examples of this all the time. This is a really common scenario, a really common way to model problems. We've got our, the irradiation is G absorbed is equal to, alpha times T surrounding to the fourth power times sigma, Because that is the amount of energy, the radiative, the emissive power of the surroundings, and we're absorbing some portion of that. The emissive power, E time is equal to epsilon times T of the surface to the fourth power times our Stefan-Boltzmann constant, which means that the heat flux can be reduced to Q double prime radiation is equal to sigma Ts to the fourth minus alpha T surroundings to the fourth, all times are constant. And since alpha and our emissivity and absorptivity are equal to one another, right? Our gray body assumption. So alpha is equal to sigma. We can just say that this is equal to times epsilon is epsilon times sigma times Ts to the fourth minus T surroundings to the fourth. Okay, so that is our net, right, heat flux out from a surface. And if we have a fluid between these two things, right? Fluid at T infinity, okay? Flux Q double prime equal to Q double prime radiation plus Q double prime due to convection, which is going to give us our epsilon sigma Ts to the fourth minus T surroundings to the fourth plus our H combined times Ts minus T infinity. So again, if we looked at this quantity, we would see that it's positive if for heat flux taking thermal energy away from our surface. But this is useful. We can work with this, right? So let's do an example that deals with exactly the situation. A combination of radiation and convection. Let me grab okay. So this is a modified problem that I found in the book that I liked for demonstrating this. We're going to assume that we're dealing with a piece of like solid state electronics. So we've got this chip here, the silicon chip, that is being powered, okay, at a rate of P electric. Our goal is to figure out what that electrical power is, okay, basically what the maximum chip power is to maintain steady operation with this chip at 85 degrees Celsius, right? And if it's enclosed in a box filled with air, where both the air temperature and the surrounding temperatures are at 25 degrees Celsius. This is a pretty good, analogy to like what our, the chipset in a phone or a laptop might be experiencing, right? Anyone who's done like temperature monitoring on electronics, 85C is about as hot as you want most of your integrated circuits to run. We're also going to assume that this chip is attached to a backing that is a perfect insulator. Okay, this is a little bit of a departure from reality, but the idea is that there's no conduction going on. This is thermally decoupled from the substrate, okay, the circuit board that it's attached to. And finally, we're going to assume that right? That the has a combined convection coefficient of 250 watts per meter squared Kelvin. Okay. We're given our chip dimensions. It's a square, 15 millimeters on a side, which means that it has an area of L squared, 2.25 times 10 to the negative fourth meters squared. We're not worrying about the surface area on the sides here because we're going to assume this is a very thin little wafer. And we're not worrying about the back because that back side is insulated up against an insulated surface. So we're only shedding heat from this front-facing side of our chip. There we go. Okay, so we're going to go ahead and state out our givens here. So our surface temperature, 85 degrees Celsius. We're going to want to start getting into the habit of working in absolute temperatures, though, because it turns out I should have written this above, but our radiation expression for our T's there, that, right, requires that we use absolute temperature. It's the whole idea. Anything above absolute zero radiates energy. So you want your radiative heat flux to go to zero when your temperature is equal to zero in an absolute sense. So we're working in Kelvin in this case. So 85 degrees C is 358 Kelvin. Our T surroundings is equal to, right, our T infinity is equal to 25 degrees C, which is equal to 298 Kelvin. We've got our combined convection coefficient of 250 watts per meter squared Kelvin. We've got that our emissivity and absorptivity are both equal to 0.6, right? That's given over here, right? Emissivity of 60%. And we want to find the maximum power for this chip. Yeah.
How do we know that we can make the assumption that epsilon equals alpha in this case?
Because it said, let me scroll up a little bit. Treat the chip as a gray surface. That is the definition of a gray surface, where the absorptivity and emissivity are the same. Okay. A few assumptions to list out. Right, large surroundings. Small chip, which means that we get to treat our enclosure as a black body radiator. As I said, we'll be looking at the reasoning behind this much later in the class, but this is something we want to start to build into our repertoire as a common assumption. We can assume steady state here, because the question is how much power can we feed this chip for it to maintain a temperature of 85 degrees C in those with the 25 degree surroundings. Right. So this means that our E dot stored should be equal to 0. Our E dot stored total should be equal to 0. And then we'll restate chip is a gray surface. Alpha is equal to epsilon, and perfect insulation on the back of the chip. No conduction. Okay. So with these assumptions lined up, we're in a good spot to basically draw. We're not doing free body diagrams. We're doing sort of heat transfer diagrams, which means energy entering and leaving our control volumes. So let's assume we've got a control volume that encloses our chip. Oops. There we go. And our energy entering and leaving, what do we have? We've got Q due to convection, all right? Signed, we'll do Q double prime due to convection. Signed outward, no, actually not double prime, because we're talking about total power. And we know that our chip is warmer than the surrounding fluid. So we can be pretty confident that that convection is going to be removing thermal energy from our control volume. We've also got Q radiation out, which is going to be equal to E times the area of the chip. We've got Q radiation in, which is going to be equal to the absorbed G times the area of the chip. Okay. And what other energy sources do we have? Like how else is energy entering or leaving this control volume? Like what else might show up in our energy balance when we do our first law of thermo? Why is the chip generating heat in the first place? There's, yeah.
Electricity applied to it.
There we go. The electric power that is entering. All right. We are interested in looking at energy conservation per unit time, which means we've got electric power entering as well. That factors into our energy balance. So what we need to do is recognize, right, we've got our assumption of steady state, so we know that the total energy in this box here stays constant. We've got temperatures we can use to figure out how much of that is leaving through convection per unit time, how much through radiation, how much is coming in through radiation, and then figure out P electric to balance out that energy conservation statement so that our E dot sums to 0. Pretty simple, pretty effective. Solution, right? So we're working from our governing equation. It says E stored total is equal to 0, which is equal to E dot in minus E dot out, right? 0 because we're working with a steady problem. What makes up our E dot in? We've got our electric power plus our Q radiation in. So that is P electric plus G absorbed times A. E dot out is made up of our Q convection, A plus Q radiation out. Q convection plus E times A. So let's just throw that all into our governing equation right here. It means we've got our P electric plus absorbed G times A minus Q convection minus E times A should be equal to 0. And let's isolate our electric power. Convection plus E times A minus G absorbed times A. So it's saying to maintain a steady temperature, our electric power can be equal to all of the thermal energy that we are shedding through convection and radiation minus the thermal energy that's being absorbed from the surroundings through irradiation. Now let's plug in our rate equations for each one of these. Okay. Yes, that's a minus there. Yeah. This is going to be equal to, H times Ts minus T infinity times A, there's our Q convection, plus sigma times Stefan Boltzmann constant times the surface temperature to the fourth power times A, so there's our emissive power, minus alpha times the Stefan Boltzmann constant times T of the surroundings to the fourth power times our area. And now, we get to say, guess what? Alpha and sigma, and epsilon are equal to one another. So gray, epsilon equals alpha, and we can simplify this down to H times Ts minus T infinity plus, epsilon sigma times Ts to the fourth power minus T surroundings to the fourth power, all times our surface area. So we've got, this is our Q double prime due to convection. This is our Q double prime net due to radiation. We can plug in our 250 watts per meter squared Kelvin times our temperature difference here, so our 358 K minus 298 K plus 0.6 times 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the fourth, there's our Stefan Boltzmann constant, times Ts, so there's our 358 Kelvin to the fourth power minus our 298 Kelvin to the fourth power. And this is all going to work out to 3.375 watts for our convection part plus 0.065 watts for our radiation. So this means our chip can be powered with up to 3.44 watts without exceeding that 85-degree temperature. Okay. This actually is a nice little, yes?
Do you have the area?
Oh, sorry, I forgot the area in there. All times 2.25 times 10 to the negative fourth meters squared. Let me zoom out just a tiny bit and rewrite that. 10 to the negative fourth meters squared. Thank you. So this is a pretty good analogy to, the cell phones that you put in your pocket, but not where we're really limited, by the power that we can dump into electronics. We're really limited by the ability to dissipate that power through thermal processes. All right, we're going to come back on Friday and dive headfirst into conduction and the heat equation, which starts off chapter 2. We'll see you then.